Welcome to video 10 about parallel resonance circuits. Circuits made up of a resistor, inductor, capacitor. Here we see a parallel resonance circuit. Notice that the source is a current source with a current value and zero phase shift. When we look into the circuit pins, the complex impedance we see is ZP, and we notice that all components are in parallel, so the circuit would behave similar to some resistors in parallel. We just have to remember that the capacitor and the inductor are complex, so they have two properties each. The capacitor can be an open circuit and a short circuit, similar to the inductor can be a short circuit and an open circuit. But the resistor is pure ohmic, so this will not change value over the frequencies. The important parameter in the circuit are the currents into the components, because we will have a current sharing. Current comes from the source will be shared between the individual components. In order to validate the circuit, we use, as always, the DC frequency, 0 Hz, the resonance frequency, and a frequency that's infinite. If we consider that the source frequency is at DC level, so 0 frequency, then we can see that the capacitor will act as an open circuit, and due to the wiring of the inductor, it will act as a short circuit. So the current out is minimum because we have a short circuit. All currents from the source will actually go through the short. And therefore, the current in the resistor is 0 because it's all going through the inductor. So we'll get a V out of 0 because there is no current times the resistor to give an output. Then we consider the resonance frequency. And here at the resonance frequency, when both of the capacitor and inductor is at resonance, they cancel each other out. They have opposite phase shift, and thereby canceling it out, and then all the current from the source will actually go through the resistor, and we will get an output saying the phase current from the source times the resistor is actually the out. Then for the frequency is infinite, then the capacitor is short circuit, but due to an infinite frequency, the inductor is open circuit. So here in this case, at higher frequencies, the capacitor is shorted out and the inductor is open circuit. Because of the short circuit, all the current from the source will go through the capacitor short, and therefore there will be no current to the resistor, and therefore 0 current times a resistance is still 0 V out. This is the properties of the parallel resonance circuit. Coming to the equations for it. When we want to find the impedance looking in between these pins, we treat the circuit as parallel components. So this is a complex impedance, and also this, but they are in parallel with the resistor. From electronics in general, we know that um, 1 over the impedance of each we can add together. So here we have the impedance of the conductivity of the resistor, the conductivity of the capacitor, and the conductivity of the inductor. As you can see, they are summed up here. We have the definition of the resonance frequency. It's the same as for the series resonance circuit, but it's defined at the frequency which the impedance is purely resistive. The total imaginary parts in the denominator is cancelled out, so this part cancels this part out. This is then the consequence. This part here becomes equal to this part. Another component thing we need to know is the quality factor for the parallel resonance circuit. In relationship to the resistor, the inductor factor is the resistance over the inductor equation. For the quality factor for the parallel, together with the capacitor, it's 2p, the resonance frequency, times C times R. The frequency, so to speak, the transfer function of the parallel resonance circuit can be found as the resistor over 1 plus J compared to the parallel quality factor, and then F over F0 minus F0 over F, treated by the quality. The output voltage is, of course, the input current times the resistor divided by the parallel impedance of the circuit. When we look to the bandwidth, it's also defined as the resonance frequency divided by the quality factor of the circuit. So here the parallel quality factor. The bandwidth is still the higher frequency part minus the lower frequency part at the half power components, meaning where the output is lowered to minus 3 dB. If the quality factor of the circuit is over 10, we can use the approximations for the higher bandwidth frequency as the resonant frequency plus the half of the bandwidth, and for the lower frequency level we can use it as the resonance frequency minus the half of the bandwidth. We can see that the current times the resistor output is also dependent. If we look to the scaled frequency at the resonance frequency, if the running frequency we are having is the same as the resonance frequency, we will have a maximum voltage out based on the current and the resistor. As we go down in frequency, so the frequency becomes smaller than the resonance frequency, we can see that the frequencies are not having a very big amplitude. And if we come higher than the resonance frequency, it's the same the case. The higher the frequency over the resonance frequency, the less the amplitude of that signal, that specific frequency is coming out. It's again dependent on the quality factor of the resonance circuit, similar to the series resonance circuit. Something we have to notice is that the currents here, because we use a current source, the current through the inductor and the capacitor is Q times bigger, the quality times bigger than compared to the current in the resistance. And that's actually the source current. So the source current will run in a resistor, but a quality factor higher current will run in the capacitor, and similar, a quality factor higher opposite current will run in the inductor. But due to that the currents in the capacitor and inductor is opposite, they will cancel out, and effectively we will only see that the source is delivering the current compared to the resistor. End of video 10. Thank you for watching.